Right. Welcome to this explainer. Today, we're exposing a massive secret. That periodic table hanging on your classroom wall, the one you're desperately trying to memorize, it's not quite as perfect as you think. More importantly, if you're in the 9th to 12th standards, I'm going to show you exactly how to master the bits you actually need to know without completely tearing your hair out.
Because right off the bat, we have to ask a genuinely shocking question. What if that rigid, perfect grid you've been staring at during chemistry class is actually riddled with compromises and intense scientific debates? I mean, it looks like this definitive, flawless map of the universe, but the reality is significantly more complex.
Let's dive straight into part 1, the illusion of the perfect grid.
So here's the fundamental issue. Elements naturally follow a continuous sequence. You can think of it like a flowing, endless ribbon of complex quantum behaviors. But to fit all of that neatly onto a standard two-dimensional page, pioneers like Dmitri Mendeleev literally had to take scissors to that ribbon and introduce artificial breaks. The standard 18-column table we all use today is basically just a flat page compromise. It forces a rigid, rectangular geometry onto something that naturally just wants to flow without interruption.
You can see exactly what I mean with the infamous Group 3 controversy. Countless textbooks mistakenly place lanthanum and actinium right there in the middle of the D block. But physical and quantum evidence overwhelmingly shows that it should actually be lutetium and lawrencium. Dropping those two in keeps the D block completely continuous and avoids a really awkward split. This is fiercely debated by chemists at the highest levels, yet you'll probably still see the flawed version hanging in your classroom tomorrow.
And then there's the massive identity crisis of our very first two elements, hydrogen and helium. Hydrogen is traditionally shoved into group 1 just because it has one valence electron, but it forms diatomic molecules and hydride anions, which means it behaves exactly like a group 17 halogen. And helium? Well, it acts like an unreactive noble gas, but its actual electron configuration perfectly matches a group 2 alkaline earth metal. It is a massive placement headache for chemists.
Because of all these structural headaches, scientists have come up with some brilliant, almost sci-fi-looking alternative models to better match the mathematical realities. You have the left step, or Janet model, which shifts the entire S block to the right side to perfectly match electron shell filling. Then there's the Adama table, which is this crazy tetrahedral tower-like format based strictly on quantum numbers. And my absolute favorites are the spiral models. These eliminate those artificial breaks completely, presenting the elements in a continuous sequence that expands outwards from the center, almost like a galaxy.
Which brings us neatly to part 2, stop memorizing every single element.
Seriously, validating all these flaws is brilliant news for you as a student. It means you can stop stressing about blindly rote learning all 118 elements. Top chemistry educators point this out all the time. Treating the periodic table like a random phone directory is a huge mistake. Don't memorize, understand. The table is a map of trends. Grasping how it's organized, understanding the group numbers, the blocks, the reactivity trends, is infinitely more valuable than just sitting there chanting atomic weights to yourself.
If you're in the 9th to 12th standards, here is exactly where you should focus your energy. Look at this priority breakdown. You want to intimately know the high priority groups, groups 1 and 2, which is the S block, and groups 13 through 18, the P block. Then mix in the medium priority stuff, which are your most common transition metals like iron, copper, silver, gold, and zinc. And those lanthanides and actinides floating at the bottom, keep them strictly on the low priority list. They rarely form the core of your exams, so you can just look them up when you actually need them.
So, how do we actually lock this in? Let's move to part 3, 4 interactive tricks to learn it.
Trick 1 is prioritizing structure over the tiny details. Rather than reading it like a book from A to Z, read across the horizontal periods for electron counting. As you move left to right, atomic numbers increase. Then read down the vertical groups to spot elements with identical chemical behaviors, meaning they're going to react in the exact same ways. Finally, visually group the table into its S, P, and D blocks. Once you see that macro structure, you can predict how an element will react without ever memorizing its specific profile. Trick 2 is using quirky mnemonics to chunk that data together. Let's take the first 10 elements: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. You can turn their symbols into a silly, highly memorable sentence like, "Hungry hippos love big bowls, cats nap on fluffy nests." Simple, right? And speaking of smart shortcuts to boost your grades, Academic Zenith Online Academy currently has their admissions open. You can book a free demo class today and avail a 30% discount on any course. Definitely worth checking out. Now, back to our tricks.
Moving on to trick 3, vivid visualization. The human brain remembers bizarre images far better than abstract letters. Picture a bright red floating balloon bouncing against a ceiling. That's hydrogen. Now imagine inhaling from a balloon and suddenly speaking in a ridiculous high-pitched voice. That's helium. Think of the hot rechargeable battery tucked inside your mobile phone for lithium. And for carbon, visualize a really sharp pencil sketching darkly on paper. By attaching these vivid, sensory mental images to abstract symbols, you lock them securely into your long-term memory.
Finally, trick 4 is active recall and diagnostics. Don't just passively read the table. It doesn't work. Actively try to sketch the basic layout from memory on a blank piece of paper, filling in only the elements you confidently know. Another brilliant interactive exercise is using a periodic table of mistakes. Find a flawed table with deliberate errors, like swapped symbols or totally incorrect group placements, and play detective to spot them. Better yet, swap tables with a classmate and see who can find the most errors. Pairing this sort of active diagnostics with spaced repetition over a few days is going to solidify your recall effortlessly.
As we wrap up this explainer, I want to leave you with a fascinating thought. Right now, scientists at the 88-inch cyclotron are studying atom-at-a-time chemistry for super heavy elements at the very bottom of the table. And they are finding that these elements' placements might not actually dictate their correct chemistry at all. So as we discover even more future super heavy elements, will their bizarre quantum behaviors finally break the system entirely, forcing us to abandon the grid and redraw our map into a continuous spiral forever? It's definitely something to chew on tomorrow morning when you walk into chemistry class and stare up at that poster on the wall.